Welcome to Visual Algebra Lecture 2.12, Other Finite Groups. At this point, most of the groups that we will encounter in this course are from families or constructions that we have already seen. However, it is worth talking about the bigger picture and the impossible classification of all finite groups. Even the most basic building block groups, which are called simple, were not fully classified until 2004. In this lecture, we will pay particular attention to groups of order p to the n, where n is prime. By the end, we will encounter some facts that most of you will find quite shocking. I know I was surprised by them when I learned about them not all that long ago. Let's get started. The complete classification of finite groups is truly an impossible task. However, work along these lines is worthwhile because much can be learned from studying the structure of groups. For example, consider the following open-ended question. What group structural properties are possible? And what are impossible? And how does this depend on the order of G? One approach is to first understand basic building block groups, and then deduce properties of larger groups from these building blocks and how to put them together. In chemistry, building blocks are atoms. In number theory, building blocks are prime numbers. What is a group theoretic analog of this? There are several possible answers, and one approach, probably the most common, is to study groups that cannot be collapsed by a non-trivial quotient. These are called simple. Even though we haven't formalized this, we've seen examples of quotients in Cayley tables throughout this course. So you should have a sense as to what they are. The classification of finite simple groups was completed in 2004. It took over 10,000 pages of mathematics spread over 500 papers and over 50 years. So it was a monumental task. We'll actually summarize this in the beginning of chapter 6, though of course there's no way we're going to be able to prove even the tiniest bit of it. But to put it in perspective, I like what Grant Sanderson, you might know him as 3 Blue, 1 Brown on YouTube, says. He says that finding the simple groups is like finding the periodic table of groups. And then finding all ways to combine them is like doing all of chemistry thereafter. So just finding the group theoretic building blocks was such a huge task that the complete classification of finite groups, of course, is basically impossible. A different approach to classify groups by understanding smaller building block groups is motivated by the following idea. To understand groups of order, for example, 72, which is 8 times 9, a power of 2 times the power of 3, it would first be helpful to understand groups of order 8 and groups of order 9, and then how to put them together. This motivates the following definition. If P is prime, then a P group is any group of order P to the n. Let's look at small powers of P. Every group of order P is cyclic, and therefore abelian. We can ask, for what other integers n do there not exist any non-abelian groups? We don't yet have the tools to answer this. We will. But let's investigate for small powers of P. It turns out that there are only 2 groups of order P squared. They're both abelian. There's the cyclic group, ZP squared, and ZP cross ZP. What about groups of order P cubed? Well, let's start with P equals 2. There are 3 that are abelian. We've classified these. There's a cyclic group, Z8. There's Z4 cross Z2. And then there's Z2 cross Z2 cross Z2. I'm writing it with P so you can see how it generalizes. There's also the dihedral group, D4, and the quaternion group, Q8. And this is it. We don't quite have the tools to prove this, but we will soon. It turns out that Something like this holds for all prime p's. In particular, there are always 5 groups of order p cubed for any prime p. But surprisingly, the pattern for p equals 2 does not generalize. Well, the abelian group part does. It's just the 2 non-abelian groups are going to be different. It turns out that if p is a prime bigger than 2, then there are 2 non-abelian groups of order p cubed. One of them is a so-called Heisenberg group over Zp, which is just a set of upper triangular 3x3 matrices with ones in the diagonal with entries from Zp. This ends up being a semi-direct product of Cp cross Cp with Cp. And then there's another group. I'm just going to call it GP. I don't know if it has a standard name. I don't think it does. Which can be represented as 2x2 matrices of this form. So 1 plus PM, B, 0, 1, where M and B are now in ZP squared. I don't know about you, but this matrix representation just doesn't do it for me. Maybe I'm not thinking about it the right way. I think it's more helpful to think about this as a semi-direct product of the cyclic group Cp squared with Cp. So both of these are semi-direct products. This one has an element of order p squared. This one does not. These two groups generalize from groups of order p squared to groups of order p to the 1 plus 2n. So this is some odd number. And they are called extra special groups. And here are the presentations. Now, once again, I don't know about you, but I don't take much from this. Like, they're almost the same. It's just, let's look at where they're different. This is CP, and this is just C. And then there's no equal sign here. So I don't know much about these other than these things generalize, and once in a while I'll see this name pop up every now and then. But yeah, I don't expect you to look at this and be like, oh, of course. Okay, let's move on. Here is a table showing all groups of order up to 30. And I want you to notice several things. First of all, we've seen all of these groups, or at least all of the constructions. There are cyclic groups. Well, that one's not cyclic. Dihedral groups, quaternion and generalized quaternion groups. There are these semi-dihedral, semi-abelian, and diquaternion groups. There's dicyclic groups, symmetric groups. This is SL2Z3. Remember that one. There's this affine general linear group. That's actually a semi-direct product of C5 and C4. And then, we haven't seen the semi-direct product of C3 and D4, but we know how to construct it. And there's others like that as well. Next, I want you to notice that there are a lot of groups of order 16. There are 14 of them, in fact. And then there's a lot of order 24. There are, I think, 17. Think about why that is. Why are there a lot of order 16 but not that many of order 18 or 22? Well, it turns out that there are a lot of groups of order p to the n, where p is prime and n is even moderately large. So the number of groups of order 2 to the n, well, 2 to the first, there's 1. 2 squared, there's 2. 2 cubed, we saw that there's 5. And then 2 to the fourth, there are 14. How many do you think there are for 2 to the fifth? 32. Something to think about. I'll show you the answer before the end of the lecture. Once again, I encourage you to go to the LMFDB for abstract groups. It's a great way to search. You can type in all groups of order 256 and see what it returns. You might be surprised. Let's have a little fun now and play a game. Here is a list of the number of groups of order n from n equals 1009, which is prime, all the way up to 1023. How many groups do you think there are of order 1024? Take a moment to think about this. It's a game that I would play with my class sometimes, with a little cash prize. Not too much, like $20. And the closest one wins. But there's a catch. If you underguess, you can't win. So it's the closest person to the correct answer who overguesses. Take a moment and pause this video and think about what you would guess in that situation. What if you wanted to be really, really sure that you did not underguess? Because you can't win if you do. What's your guess? You ready to see the answer? Here it is. And yes, that's not a typo. There are over 49 billion groups of order 1024. So, do you think you would have overguessed and won the $20? Or do you think you would have underguessed like almost everyone else does? I'm going to have to stop playing this game because I gave away the answer publicly on YouTube. But oh well, it's had a good run. I actually did this at the joint math meetings in Seattle in 2025, a couple weeks before recording this. And there were a bunch of number theorists in the audience, some of them who actually work on the LMFDB. And they all knew the trick. I didn't realize it. I figured some would. But even then, like, they all massively overguessed, and I don't think anybody got within multiple orders of magnitude. But it was different from what I do, in a graduate or undergraduate class where, there's like one person that sarcastically guesses 10 to the 100th and they win. Here's another fun slide. These lists show the number of p groups, that is groups of order p to the n, for the three smallest primes. So do you think you would have done a little bit better in your guess of the number of groups of order 1024 if you had seen this list instead? I think you would have. Now, there's several things about this that I find utterly remarkable that I want to just comment on. First of all, the fact that we even know these numbers, I think, is incredible. There's obviously a lot of group theory and computational things that I have no idea about. It's very niche, but it's really, really cool. So a little bit of history here. This number, the number of groups of order 1028, was not discovered until, I want to say 1980 it was first published, but then there was an error in that, so it wasn't corrected until 1990. Think about the history of computers when you see these dates. Then it wasn't until 1991 that it was determined how many groups there were of order 256. There was something called the P group generation algorithm. That was crucial. I don't know anything about this other than it exists. And then in 2002, these two numbers were determined. Well, sort of. It was published and widely accepted and appeared in GAP and I think a couple of group theory textbooks. But it was incorrect. In 2022, a PhD student, David Burrell at the University of Florida, found that there was a mistake in these calculations. They were off by 1,867, I think. I forget if they over or under counted. But he published that. He checked with the authors of this original paper, and they verified that he was indeed correct. So he published a short, 2 or 3 page note on this. It's called On the Number of Groups of Order 1024. I encourage you to check it out. He also talks a little bit about the history of this as well. I think the total number of computational hours was over 2,000, so that's like 84 days in the year 2021, 22, something like that. So it's a lot of computer power. Now, for the number of groups of order 2048, it's known that it's bigger than this number, 1.774 times 10 to the 15th, and it's known that these first 4 decimals numbers are correct. John Conway at Princeton University has said the human race will never know the exact number of groups of order 2048. And we also don't know the number of groups of order, 3 to the 8 and 5 to the 8 either. Once again, I know nothing about the math that goes into this. I find it incredible that we are confident that these numbers are right, or that even that these things are. But I do trust that the experts have spoken and checked with each other and independently verified this. A different way to characterize the incredible thing that we just learned is with the following amazing fact. There are this many, 49 billion, almost 50 billion groups of order less than 2000. Of these, 99.2% of them have order exactly 1024. If you go up to 2048 and look at the groups less than that, it's something like 99.998% of them. Yet only 6 groups of order 1024 have an element of order 512. And we've seen them all. There's the cyclic group, C1024, of course. There's the generalized quaternion group, Q1024. And then there are these 4 semi-direct products of C512 and C2. The abelian one, which is the trivial semi-direct product, the dihedral, the semi-abelian, and semi-dihedral. Here's a conjecture, which is certainly publishable in the annals if you can solve it. And it's so obviously true. It says almost all finite groups are 2 groups in the asymptotic sense. That means for any n, you take how many 2 groups there are of order less than or equal to n, and divided by the total number of groups of order less than or equal to n, you'll get 1. In other words, this percentage here is going to go to 100. It's absolutely, certainly true without a doubt, but we have no idea how to prove it. Finally, let me finish by once again promoting some of these websites that are great for exploring some of these ideas, especially group names and LMFDB. There's a few others. There's Group Explorer, which is more educational. Nathan Carter, the author of Visual Group Theory, wrote it. Check that out. It's great for like a small undergraduate class. And then there's the free open source GAP program, Groups, Algorithms, and Programming software package. And there's a very nice Mac interface, gap.app, that you can download. And these programs were instrumental for the computational resources that were needed to prove how many groups there were of order 1024. And that is a good place to stop. It brings us to the end of Chapter 2, Examples of Groups. Next up, Chapter 3, Group Structure, where we'll learn about subgroups, cosets, conjugacy classes, both of subgroups and elements, products, quotients, and more. We will introduce subgroup lattices, and that will be one of our most useful visuals throughout this course. So there's a lot of fun stuff, a whole bunch of new fun visuals. So I'll see you on the other side.